Okay, welcome to office hours for the Evolutionary Robotics online course Ludobots. The home for the course is located at the following URL. Ludobots is a hybrid course being taught simultaneously on the web and also for University of Vermont students, where it is better known as CS206 Evolutionary Robotics. I'll be online for the following hour if you're taking the class here at UVM or you're following along the course online. Please go ahead and ask a question in the chat window for the MOOC at any time, or sorry, for the Twitch at any time. When a question appears, I will take some time and answer it. In between questions, I will continue on implementing a series of increasingly powerful optimization methods. And today we're going to tackle an algorithm that optimizes both for some desired behavior in your robot and diversity among behaviors in the robot population. Okay, that's where we're headed today. Just to sort of back up a little bit, in previous weeks, I've walked you through a steady state algorithm, which is described by 4 steps here. The first step is to create a population of random robots. So for those of you that are following along, we've been working on a piece of Python code called moo for multi-objective optimization. If we scroll down to the main function, we'll see that there's a function that initializes all random robots and then evaluates all individuals in the population. That's step 1 in our pseudocode here. And step 2, evaluating each individual in the population. Now we're going to iterate a number of times, and at each iteration we are going to select 2 individual robots at random in the population. We are going to determine which robot wins and which robot loses. We are then going to make a copy of the winning robot. We are going to introduce a mutation to that copied robot, and we're then going to take that new mutant and replace the losing robot with the mutant and evaluate the mutant. So during this competition here between these 2 individuals, we are going to detect who wins and who loses. And the loser dies, and the winner is allowed to produce a single offspring. Okay, and then at the end of this, we're going to show the best individual in the population. So let's go back to our code for a moment. Here's our iterations. We're going to iterate several times. We're going to compete one robot against another, whichever the winner, whichever one. We're going to keep this competition going until at least one offspring is created. It's possible in this competition that it's a tie, neither individual wins or loses, in which case no offspring is produced. So we're going to continually select a pair and compete one against the other until one wins and one loses, and the winner creates an offspring. So while it's a tie, keep competing, and then print all the individuals. Okay. So how did we decide last time? I'm going to just highlight all these lines. Excuse me. How did we decide last time between who wins and who loses? Well, let's go have a look and see how that works. Let's go back to moo.py. Let's go have a look at this function here. Let's drill down into this competition. We're going to look for the definition of this function. We see we pick at random robot I, one individual in the population. We then pick another robot J in the population, and we keep picking a new J until it's not the same as I. We don't want to pick the same robot twice. We want to make sure that when we get to this line, I and J are different robots. We then introduced this idea of multi-objective optimization last time, where one individual may dominate another individual if it is at least as good, if not better, on all of the objectives we want to select robots for. So let's drill down even further into dominates. The ith individual is going to be defined in individual.py. Here's that function here where we have the self, and we're looking to see whether self, the current individual, dominates the other. We can see that it does dominate the other if its fitness is greater than the other. In our case, we're trying to evolve robots that move as quickly as possible. So if self moves faster than other, it's better on one objective. And if self is at least as stable as the other, then I, or self, is more fit and at least as stable as other. That's what we're defining as domination. In that case, self dominates other. Okay, so that's fine. That's where we left things last time. And if we run this now, we're going to run our function. I'm going to decrease the population size so we can see the entire population. So I'm going to open the constants file, which contains population size. Let's just create a population of 10. We can see very quickly that the population is taken over by descendants of robot 2. So this is not really what we want. And we've now seemed to have, we see that the code has stalled out here because we can now not find a pair of individuals where one dominates the other. So the problem we're going to address today is how do we keep diversity in the population? How do we keep the descendants of one individual, in this case number 2, from taking over? If I run the code again, starting from a different random population of robots, well, we got a bit of a coincidence here. Offspring of individual 2 took over again. Let's try running this again. When we run our code again, we can now see that it's all the individuals, all of the descendants of number 6 have taken over except for 2 survivors who are the descendants of individual 5. Okay, so that's what we're going to do today. So now instead of selecting for fitness and stability, we're instead going to compete who wins, who loses, based on desired behavior and diversity. So an individual has a chance if it moves, a robot has a chance if it moves, and the way in which it moves is quite different from other individuals in the population. So I'm going to change this word diversity here to uniqueness. How unique is robot I? Okay, so we need to define. Let's go into individual.py, and let's go into dominates again. So now we're going to comment this line out. Now we're going to define domination based on fitness. Self has to be more fit than other, and it needs to be more unique than other. Okay. That's what we're looking for. So we're going to have to define now this uniqueness value. So let's start by setting it to 0 to begin with. And we're going to have to make some changes in a couple other places. Whenever a winner wins and produces a copy of itself here, and we're storing it in this temp individual, we're going to have to set uniqueness back to 0. Okay, so every new individual has a uniqueness of 0, and after we've started to evaluate it and computed its fitness, we're also going to compute uniqueness. So let's add this new function called uniqueness. Okay, we need to add it there, and we also need to add it evaluate all. The first time we evaluate all the individuals in the population. Evaluate all. compute fitness, and compute uniqueness. Okay. So how are we going to compute this uniqueness? Well, let's go back to individual.py. You remember last time that when an individual finished, we wait for it to finish and it finishes, we collect light sensor data, and we use light sensor data to compute the fitness of the robot. So the robot is moving towards a light source, and as it gets closer to the light source, the light sensor value becomes greater and greater. So the greater that light sensor value, the more fit this robot is. We then grabbed touch sensor data and we stored it in a 4 by 500 matrix. So we've got 4 rows and 500 columns. So the element ij in this matrix represents the value of the ith touch sensor at the jth time step. Yeah? Okay. We use that touch sensor data to compute the stability of the robot, more or less how much time the 4 feet, which have the 4 touch sensors in them, stayed on the ground. Okay, so similarly, we're going to use touch sensor data to compute uniqueness. So we've computed fitness here. Now we're going to compute this uniqueness. So we're going to do it from touch sensor data. So again, we're storing all of the touch sensor data, or storing the touch sensor data in here. And then when we're done with the touch sensor data, which was stored touch sensor data was stored in the simulator, we delete the simulator. So let's just print the touch sensor data that we've grabbed back and exit for the moment. Okay. Let's also just scale things back for a moment. Let's set our population size to 1 and the number of iterations to 1. Okay. Let me make one more change here. Let's play blind equals false so we can see what's going on. So we start this up. We have a population of 1 robot. Here it is. Here's our robot doing its thing. And when it's done, here's the touch sensor data we get back. Here's the touch information over time for the first foot, touch information over time for the second foot, touch information over time for the third foot, and finally touch information over time for the 4th foot. Okay. Okay, what we're going to do is we're going to take this matrix, touch sensor data, and we're going to compare it against the touch sensor data in all the other robots. And the difference between robot I and robot J is the Euclidean distance between their two touch sensor data matrices. So it's really the different ways in which the robot touches the ground. Okay, so in order to do that, though, we're going to compare I against all the other individuals, and we're going to look to see which other individual J is it closest to. In other words, which other robot J in the population has the closest touch sensor data, and that distance is the uniqueness of robot I. If the closest robot to I is, if the closest robot to I is robot J out here, and they're quite different in how and the two robots I and J are quite different in how they touch the ground, then I is pretty unique. If, on the other hand, we have a robot I and there is another robot J, and its touch sensor data is very similar to the touch sensor information in I, then I is not very unique. Okay, so we're going to have to compare. The touch sensor data from I against all the other individuals. So we're going to have to change this a little bit. We're going to store touch sensor information in robot I itself, and we're going to use it later. Okay, so we're going to change compute compute uniqueness to store uniqueness. Okay, so let's go back to eval for a moment. Evaluate all. We're going to compute the fitness and then store the uniqueness, and then we are then going to compute then for each individual in the population, after all of them have been evaluated, we're going to compute uniqueness for individual I. Yeah, you'll see that this function is at the level of actually should be at the level of population. Okay, so we're going to take I and we're going to compare its uniqueness against all the other individuals in population. Yeah, make sense? Okay. So let's go back to evaluate all, compete one against one another. Okay, we need to store the uniqueness of the loser and then compute uniqueness of the loser now, right? And again, we need to do it at the population level. Okay, so let's go into population now. And we are going to compute uniqueness of robot I against everyone else in the population, right? So for j in range 0 to pop c dot pop size -1, we're going to compare or compute distance from individual j. Okay, so current distance is this. We're going to define the uniqueness of this individual. We're going to set its uniqueness to a very high value, or sorry, uniqueness to a very low value. We need to also make sure that j is not equal to, if j is not equal to I, then we can do this. Take the distance between I and j in terms of their, take the distance between I and j in terms of their touch sensor data matrices. Take the distance between them. If the current distance is greater than I's current uniqueness, then we set the uniqueness to be equal to the current distance, right? I think actually that's wrong. We want to do it the opposite way around. So let's start by defining uniqueness to be a very high value. Take the distance between the way in which I moved and the way in which j moved. And if that distance is smaller than the current uniqueness, we set the uniqueness to the current distance. So uniqueness is going to be equal to the minimum distance between I and any other robot j in the population. Okay, that's how we set uniqueness, and we're done. Okay, last thing we need to do is define this function, compute distance from. So that's at the individual level. I there. So we go into individual.py and we compute distance between self and other. And we know that each one has a matrix called touch sensor data here. Self.touch sensor data. And we know we also have the other individual's touch sensor data. We want to take the Euclidean distance between these two matrices, and on my other screen here I'm going to look up how to do that in NumPy. So the Euclidean distance between self and other, let's just call it Euclidean distance, is equal to numpy dot, we're going to use linear algebra, and we're going to take the norm between this matrix and this matrix. That'll give us the Euclidean distance between these two. Let's print the, actually let's just return Euclidean distance. We'll check it later. Okay, so let's go back to population now. We're computing the uniqueness of. So every individual now is going to have its own uniqueness score, where the lower the uniqueness score, the less unique it is. Okay. So let's go back to top level. Just remind ourselves where we are. We're dealing with this competition. We're using this dominates function to determine whether I dominates J. So let's go back to individual.py. And we're going to assume that self dominates other if self has a higher fitness than other and it's more unique than the other. Okay, I'm just going to delete these so they're not confusing us. Okay, let's go back to the top level. We want to print all as well, so let's make sure we print out this uniqueness score. So instead of stability, we're now printing uniqueness. Okay, let's see what happens if we run our code now. Remember we just have one, and we can't compute its uniqueness against anyone else. There's only one individual in the population, and we get a error here. Let's see, what did we do wrong here? Individual. We're not using the population function. Okay, let's think for a minute. We're going to just do the following. I'm going to take this out and put it right into mu.py. Okay. I apologize. You can see that I'm not using a Python editor. I'm using Vim because I'm old-fashioned, but I think that should do the trick. Okay, and we need to change these to pop I. And pop J. Okay, we need to at least increase the population size to 2. Actually, let's put it back to 10. And let's just do one iteration to start with. Okay, we have our 10 individuals that are being evaluated, our 10 initial random individuals, and each of them is going to get their own uniqueness score. Okay, we still got an error here, compute uniqueness for. Compute uniqueness of. Right. So just to remind ourselves, we're evaluating every individual in the population, storing the, not storing uniqueness, we should probably rename this, store sensor data. Store sensor data, and we have that somewhere else as well. Store down here. Okay. Let's also make sure that we turn off the graphics. Play blind equals true. Okay, let's keep going here. We've still got some more errors. Takes exactly 2 arguments, 1 given. Oh, yes, we no longer need this. Okay, let's keep going. Compute distance from J. Compute distance between. Okay. Compute distance from self-data. Actually, between is better, I think. Hopefully that'll do it. No? Oh, right. Okay, so here we go. So we can see if we look at our initial random, our initial population here. Actually, I take that back. It's not our initial population. It's after 1 iteration. Okay, let's have a look and see what's happened here. If we look across here, we can see that individual 6 has replaced the original individual 0. So 0 was the loser, and 6 was the winner in this competition. Let's have a look here and see. Let's actually. I'm gonna make a few changes here so we can really see what's going on. Let's not iterate at all. We're not even going to do any competitions, and we're going to print all at the beginning. Okay, so here we go. Here's our initial population of 10 random robots. Here's their ID numbers. Here's their fitness, or how close they get to the block, the light source. Higher is better. And here's their uniqueness. So if we look down this column here, we can see that individual 4 here got the closest to the light source. So the highest fitness compared to the other 9 individuals in the population. And it had a uniqueness score of 23. So it was certainly more unique than some other individuals. But it was also less unique than some other individuals. So let's actually compare individual 4 against individual 3. We can see individual 3 moved slower than individual 4, but individual 3 was more unique than individual 4. It moved in a more unique way compared to the other individuals in the population. So in that case, if 4 was competing against 3, it couldn't kill it. It was better in terms of fitness, but worse in terms of uniqueness. If we competed, for example, individual 4 against individual 2, we'd see that 4 moved faster than 2, and 4 was more unique than 2. So if 4 competed against 2, 2 would die, and 4 would produce a mutant in 2's place. Okay, let's go back here and do a number of iterations. Let's just do 5. And that's trying to play back the best one, so we won't pay attention to that one for now. Okay, after 5 iterations, we can see that there are a number of individuals of number 2 here, several 2's, and we can see that 2 has a pretty low uniqueness score, right? Not surprisingly, because it was produced from the original number 2 here, which actually had a pretty high unique score. This reminds me now that every time an individual produces an offspring, we need to recompute the uniqueness of 2, of the parent, right? Because the parent, not only is the child very similar to the parent, but the parent is also probably similar to the child. So every time a parent produces a child, it's quite likely that the parent's uniqueness score will go down. So how do we make that change? Well, we go back to where the competition occurs. One against another here. Assuming that a mutant is produced, it we compute the uniqueness of loser, and then we need to recompute the uniqueness of the winner, right? Which was the one that produced, the winner produced an offspring. Okay, let's again run this for just 5 iterations. And our program has stalled out because it can no longer find an individual that is that dominates another. It's trying to compete pairs. It can never find one that dominates the other. So let's make, again, another slight change here. Let's go back to individual.py and go back to the dominates function. Let's make things a little easier. One individual can dominate another one if its fitness is better than the other and if its uniqueness is greater than or equal to the other's uniqueness. We'll make it slightly easier for one individual to dominate another one. Okay. That should let us run for a while. Okay, there we go. So let's have a look now and see what's going on. Okay, we've had a number of, here's one competition. 0 competed against 1 down here. Because you can see, actually here, you can see that 1 is more fit, moves closer to the light source than 0 moves closer to the light source than 1. And 0 is more unique than 1. So 1 died out and was produced by a mutant of 0 that has this fitness and this uniqueness. Okay. And here's a version of 6. 6 has produced 1 offspring and so on. Okay, so let's run this for a while now and see what happens. Let's run this for 50 iterations. Okay, so again, we see that we get something that has pretty high fitness, 0, but we see lots of different uniqueness scores. So although these are all descendants of 0, they're all quite different. They all move quite differently from one another. And we can actually see this if we go back down here and say evaluate all, but we play blind equals false. We want to see all of these individuals. Play blind equals true. Play blind. Play blind. Okay. I believe if we do this now, after 50 generations, it's going to play back all individuals in the population. And we should see that they're somewhat different from each other. Maybe not that different. Let's have another look here. 1, 2, 3, 4. Bless me. Okay, so maybe not as different as we would have liked. Let's run this for a little bit longer. And let's increase our population size a little bit. Okay, so now we're running up to 500. Let's see how this goes. You might have seen some uniqueness scores of 0 in here. This means that there's some other individual in the population that moves identically to that individual. Should notice that there's always pairs of zeros, right? Or at least 2 zeros, because if one is identical to the other, that's identical too. Okay. Well, these do not look very unique to me. Okay, so I wonder if something is going on here. Actually, you can see here these 2 individuals are identical. And here's another clone and another clone. Okay. Let's try something else. Let's go back to individual.py. Let's see if we can fix things a little bit. Let's make domination stricter again. We really want to make things, we want to make sure that one dominates another if it's more fit and more unique. We want to put more pressure on improving uniqueness. In order to do that, we're going to have to increase the size of our population again. Let's leave it at 20. Let's see if this works. Let's see if it stalls out. It looks like we're still doing pretty well here. Okay, that seems to be working. So you'll notice that we're not converging now on descendants of just one lineage. This descendant of 10 is holding out because it's the most different from everyone else. Okay, those look quite a bit different to me. Let's really see if we can have a look at this. Let's say play paused equals true, so they'll all start paused at the end. Now we can really watch all 20 and see how they do. Okay, just a reminder for those of you that are just tuning in, this is office hours for the Evolutionary Robotics online course Ludobots. Here's the course home. Please ask questions at any time. If you do, they'll show up in the Twitch channel here, and I'll be happy to answer them. While I'm waiting for questions, I've been implementing an algorithm that selects for desired behavior and uniqueness. So we obtain a population of, in this case, 20 robots that all move as quickly as possible, but are also as unique as possible. Okay. Now, why did they not start paused? Well, anyways, let's see what we get. Well, we get some diversity in the population, I guess, but not as much as we would like. Okay, let's have a look and see what's going on here. Let's first of all go look for the one that has the highest fitness. 1.8 looks good. Do we see anything higher? There's another one. So this one and this one are identical to each other, but they should be as different, should be relatively, they're identical to each other. The most unique one is this one. It's got the highest uniqueness score, I believe. Yes, and does not travel as far. So that's the second individual here, the third individual in the population. So something doesn't quite seem right here. Or the way that we're computing diversity or uniqueness based on touching the ground, how these robots touch the ground, is not a good way of selecting uniqueness. We could try something else. Let's just try this for fun. Let's go back to compute the uniqueness of I. Let's say instead the uniqueness is not the uniqueness between, compute distance between. Compute distance between, we were using the Euclidean distance between the touch information. What if instead we just use the distance between fitness. Let's see what that does. See some negative numbers in here. We don't want negative numbers. So again, we go back to individual.py. Let's take the absolute value of the difference as the uniqueness. Oops. Floating point absolute difference. That's it. There we go. Okay. See that the best one in the population has a fitness of 0.2, and it has a clone down here. .3 seem to be traveling a fair bit. How is this doing? This helped a little bit. Okay, it's a little hard to see, so let's make sure play paused equals true, play blind equals false. That's why they weren't starting paused. Okay, let's try this again. All right, again, while we're waiting, if anybody has any questions about the online course Ludobots, go ahead and ask them. In between questions, I am trying to show you how to optimize desired behavior and uniqueness. So here's desired behavior, which is speed. The higher the number, the better. And uniqueness here is how different an individual is from all the other individuals in the population. Again, the higher, the better. I think we're making a little bit more progress here. Okay, now we've got them all paused. Let's just have sort of look at pairs of them as we go and see how we're doing here. Now, these don't look too unique to me. How about, we'll watch number 3 and number 4. Okay, so a little bit of uniqueness, but not too much. Maybe we can do better. Let's have a look at one more pair here. Okay, so using fitness as a way to determine uniqueness doesn't seem to work too well, right? We're definitely getting things that are very similar to one another, so let's just shut all these down. And let's go back to individual.py. Let's try determining uniqueness again based on something else. Let's take total time feet spent on ground as the sum of all touch sensor data. Let me just make sure I got that right. I'm looking to see how to sum all of the elements in a matrix. Let's try, I think that should do it. Let's just try and print this out. Feet spent on ground and then exit. Okay, that's it. So this is in that 4 times 500 matrix. The touch sensors in that robot fired 1,446 times. Okay, I think this might be a good one to use, although seems to be a little bit tricky. Total time my feet spent on the ground. And we want to also know the total amount of time that his feet spent on the ground, him being the other that we're trying to dominate. And the Euclidean distance is now going to just be, again, the absolute difference between these. Okay, let's try that. Notice we have some pretty high fitness values in here now, and there's a good spread in these fitness values. This makes me feel like we're making a little bit more progress here. Let's have a look. These look pretty different. Let's look at another 2 random individuals in the another two individuals in the population of evolved solutions. They also look quite different from one another. Okay, I think we're making progress here now. Here's one which is perhaps quite unique but doesn't go anywhere. We should be able to find this guy in the population. Let's have a look through here. Hard to say here. Maybe the 140. You'll notice that these, which have relatively... here we go. 0.11. That's the guy that we probably just saw. Moved very slowly and was quite unique compared to a lot of the other individuals in the population. Okay, I think now we're really starting to get somewhere. Let's have a look at some more. Okay, so you can see now that we're clearly getting robots that are much more diverse from one another. And by spreading out in the space of all possible behaviors for this robot, we helped evolution to explore more of the space and ultimately find some really good solutions, like the best one in the population. Let's run this again to make sure this isn't a fluke. You'll notice that we start out with 0.10, 0.11, 0.12. So that 0.44 that we got in the previous run was much better than a lot of what we'd seen before. Let's see how we do this time around. All right, we got a 0.22 here, 0.224, 0.25, 0.26, 0.279, and that might be it for this run. Here's again a very low, let's keep 0.3, 0.33. So again, we're helping to increase the diversity in the population, which is also helping us to find These guys aren't too different, but actually quite different in the end. Okay. So you'll notice, for example, something like this, which has pretty high fitness, is not that unique. And the most unique individual in the population, this one, actually has a pretty good fitness value, pretty low, 0.08. Okay. So getting some interesting individuals here in the population. Okay, let's switch our code around. So again, instead of evaluating all, we're going to play back the best individual in terms of fitness. Show best. Okay, show best. Okay, very low uniqueness scores. There's a pretty high uniqueness score. Again, 0.1, 0.11, 0.13. We're starting to climb now. We can see some 0.15s. Still stuck around 0.15. 158. Okay, perhaps we didn't do as well on this run as in previous cases. There's a 0.16. Okay, let's watch this one. It's probably not that impressive. Interesting gait. Let's try running this again. We've got 5 minutes left, so we'll just do a few runs and sort of see what kinds of things we can come up with. So one of the things I hope you take away from this hour is that we can use multi-objective optimization to select for different properties, like the behavior itself, but also other things like how the robot moves, and more particularly, like we did in this hour, how uniquely it moves compared to the other individuals in the population. But choosing that uniqueness property, how to measure that uniqueness property, can be a little tricky. It's not always obvious how to measure uniqueness of individuals in the population, how novel or how interesting they are. All right, we've got a 0.23 here, 0.23, doing pretty well in this case, 0.26, not bad. Seem to have gotten lucky with that run where we got to 0.44. Okay, not bad. And then flipped over. Okay, so I think we will end here for today. I've shown you an algorithm to compute, to optimize for two objectives, desired behavior and uniqueness. Next week, I will show you another way of defining uniqueness that hopefully will do a better job of getting evolution to spread out and simultaneously consider robots of very diverse behaviors to find one or a few that through subsequent mutations produce high fitness, the desired behavior. So hopefully this today has shown you the challenge of defining uniqueness, and I'll try and show you a good way to do that next week. Thanks very much for tuning in, and we will see you then.